Fellow of Indian Academy of Science, Bangalore in 2004, Indian National Science Academy, New Delhi in 2016, National Science Academy, Allahabad in 2018 are other jewels in his academic crown. He is a proud recipient of J.C. Bose National Fellowship by DST Government of India 2017 and US India Professorship of American Physical Society 2009. His varied research interests include dynamics of active matter, numerical methods of complex fluids, entropy crisis, phase transitions, mode coupling, and slow dynamics. He is actively engaged in several international research collaborations in USA, Japan, and France. A dynamic physicist with more than a century of research publications and enormous research experience, I'm sure Dr. Das will make your lazy Sunday mornings as academically exhilarating as possible. I now invite Dr. S.P. Das to share his pearls of wisdom with all of us. Sir, please.
Thank you. First of all, let me thank Dr. Vinod Ashokan and others for inviting me to make this presentation of our research. This work, I'm going to, generally in this kind of talks, we say number of collaborators. Today, what I'm going to talk is more of a review or overview of things. So in principle, I should acknowledge everyone, starting from my thesis advisor, Professor Mazenko in University of Chicago, then all my students, my other collaborators, Akira Oshimori in Japan, and others. Let me move on to the talk. First of all, this is a discussion of or a course, as I'm told, of condensed matter physics, current trends of condensed matter physics. So I thought I'll give a little sort of synopsis of what this, the very basic idea of this talk is. Generally, we talk of three states of condensed matter. Here, I'm not talking about charged or ions or electrons, particles getting charged, but just in atomic level. First of all, there is the solid state. Let's say, let me move from the left. It's the gaseous state in which all the particles are randomly moving around. The density is generally low. At some low enough temperature or high enough density, it condenses into a liquid phase where the particles are more close by and more coherent, though both are disordered states. And then if it is cooled or compressed even far enough, it goes into a regular solid state. By solid, I would, in this talk, time and again come back to two kinds of solid, crystals and amorphous solids. Now, here I have just shown you a cartoon of the regular solid, like some regular arrangement of the atom. So the basic phenomena that is happening is, here you have a disordered set of particles moving around at random and colliding, but low density. So the average distance between particles, which we call mean free path in our elementary education in physics, this is quite large. Whereas in liquid, it is relatively smaller, it's more coherent. When it goes to the solid state, of course, the particles are localized. Now, when I'm going to talk about theoretical models here, so one very basic issue that one faces when one formulates systems like this, many particle systems, that is, you need some, there are effects which get large, and one has to deal with large effects. Often it is nonlinear physics, so you need some small parameter to do a theory, like you do a perturbation theory or something. Now, as you can see, in case of a gas, you can take the mean free path, which gets large. So the inverse of the mean free path can be treated as a small parameter. When you are in the crystalline phase, then the particles are around some mean position, they are moving, but they are settling there. So you can take the displacement from the mean position as a small parameter. So there are, in the solid and the gaseous phase, there are small parameters in which the theory is generally formulated. The problem is with liquids, that when you deal with liquids, you see that there is no such small parameter. The problem gets more complicated or more staring at you, that when you are dealing with super cool liquids or things which are very dense, and things goes to a situation where this system, instead of forming a regular solid, it forms an amorphous solid. So it's strongly correlated liquids, or you can say strongly correlated, so strongly correlated that it is frozen into a glassy sort of state. So formulating such theories would require looking into non-local. That means whatever is happening here is related to what is ever happening at other particles, and of course non-linear. This I'll explain more as I go on. So this is the theme of this, and then of course there is another thing that I want to discuss. Discuss towards the end. That is this active system. So here the particles generally are interacting with two-body potentials. I'll talk about it in a second. But if the particles are themselves self-propelled, that means they themselves generate free energy. You can think of a school of fish moving, or birds, or streams of bacteria moving, or self-propelled particles. Mechanics of such systems are also studied using similar methods as used for those passive systems. So I will, towards the end of my this is more current trends and more activities there, although this is also a very much active problem, the idea of glass formation. So the basic theme of this talk is that this famous quote of P.W. Anderson, that more is different. So I'm not going to focus on how what is happening in each particle, how both two of them interact. That's of course a very interesting branch of physics. As you go to shorter and shorter length scale, what is happening inside the atom, what is happening inside the nucleus, and all that. What we are going to focus on here, what happens when there are more of them. So how more of them makes a different physics. It's a different different regimes or length scale or time scales of physics that one is focusing on. And this is the basic theme of this thing, that how more of this many particle systems being around produces new physics, and how do we understand it. And basically I will discuss things in simpler terms. Of course this requires a bit of a technical jargon, but we'll try to avoid it as much as possible. Now let me just broadly describe that. So I've talked about passive systems. So we are generally talking about a large number of particles, or be it active type of particles or passive type of particles. For passive particles, of course, we can think of interaction between. So this is the microscopic of the system that we are dealing with. That is, you take any two particles, and so this is the interaction energy between two particles, and this is how it is changing with the distance. And generally in condensed matter system, there is a hard core. That means as you try to get close to it, the potential gets very high. It can even be simply like a hard sphere potential, that is infinity and zero. Here I have drawn a more well-known, more common thing, which is called Lennard-Jones type potential. It's a 12.6. It doesn't have to be 12.6. It can be some other numbers also. But this first part reflects the very steep repulsive potential, and this gives a long-range attractive potential. So the theories that we discuss generally takes the system at this level, some interaction particles, or The particle can be an active particle where it generates some energy, so free energy by itself. It could be in a surroundings when it is acted on by active particles. And how the physics of this kind of systems can be described in terms of, my main focus here would be discussion of models which are called field theoretic models. That means you take continuum models, you discuss things in terms of continuous variables. So instead of dealing with very large number of particles like 10 to the power 23 particles, you deal with a few properties of the system. And these are considered, or these are constructed by based on the symmetries and conservation laws of the system. This I'll go into as I go along more. What are the general equations for these sort of particles? One is if it is a passive system, and this is what we call classical Newtonian system. It satisfies Hamiltonian dynamics that we see in any classical mechanics book, that the position and the momentum. So you have alpha, the position and momentum of the of the alpha particle, and you have very large number of such equations. And there's a Hamiltonian for the system in terms of which you can describe the microscopic dynamics. Now, as you can see, this microscopic dynamics is completely reversible. These equations, as we know, if we transform T to minus T, it is completely reversible. So the microscopic level dynamics here is reversible, but as we know, at macroscopic level, macroscopic thermodynamics, we see irreversibility or friction or dissipation in the system. I'll not go here into all the details of such things, but that's standard thermodynamics. The other sort of mechanics that we are dealing with here is generally called Brownian motion or stochastic motion. That means, suppose you have a big particle, it can be an active particle or something, it is acted on by surrounding particles. It can be a big colloid particle in a fluid acted on by the particles of the solution. And so they are randomly pushing, because the inertia of this particle generally would be much higher than those smaller particles. And so they are randomly pushing this particle, which you can take varying over times which are much smaller than the time this bigger particle takes to move. So you formulate the mechanics. This started with theory of Brownian motion, trying to understand theory of Brownian motion by Langemann, Einstein, Smoluchowski, all these great physicists of earlier years. So this is like a new form of Newton equation or new form of mechanics, that the rate of change of momentum is of course, it can be like there could be a conservative type of force for which you have some potential. So bigger particles are interacting to this. So this is the alpha and nu are the bigger particles coordinates. So there are many particles like this. I've just shown once. But then it is acted on by a force. So there is a part which is dissipative, which is force, and you take the force proportional to the momentum of the particle. And if you take that, then this is the force, and then this random pulling is related to a noise, which is changing over much faster time scale. In case of active Brownian particles, of course, this become more complicated, because these particles are self-generating, so their frictional force is very different. And this is something I'll talk about towards the end, that how these sort of equations are used to study active systems. Let me go to the more classical or passive systems or classical physics. That is, suppose a system is in thermal equilibrium. So it's a large number of particles following classical mechanics. It's done with particles moving with quantum mechanics also. But it is basically a very large number of particles. And so the general prescription of classical thermodynamics or statistical mechanics, you calculate free energies, and then second law tells you that the free energy has to be minimized, and so you minimize the free energy, find out the phases of this. So as I was showing in the earlier, this figures, that you have those different phases, how to understand those phases from such models. And here, instead of dealing with each particles, because let's say now we focus on a particular problem, how to understand the physics of a disordered liquid going into a solid. And this is a transition, and whose theories were formed in the earlier decades. And one of the key contributors in this was actually Professor T.V. Ramakrishnan, who spoke earlier in this meeting. So how to describe these phases? So the continuum models were done in terms of order parameter fields. And the simplest example of this is that, think of the density. So if you take the density of particles, it can be mass density if all the particles are same, or number density, they're related. But generally in uniform thermodynamic state, we'll say that n is the number of particles, and I divide it by the volume, and that remains constant. But then one can think of these densities is a function which is changing with position and time. So then we have the total number of particles is an integral of this. Of course, if the system is closed and no particles is leaving, this is independent of time. This is like a constraint. We'll talk more of this later. But if we define such a function which is smooth in space and time, so this is like a continuum description, field description of the system. Here we have introduced a field which is a function of position time, and this is density, and this is a key field in studying the kind of systems that I will be discussing here. So we'll come back to this density field again and again, but this is the basic idea. You take it to be dependent on space and time. Then what happens is you can define different things with it, and that is the key quantities that one looks in a theoretical physics formulation of such trying to understand the behavior of such system are the correlation function. So what is the correlation function? So you have defined the density in this way, and of course the microscopic system is evolving through many states, and as it evolves through many states, it goes into different situations, and you take the density fluctuations. At each point, this function can vary. You can take Fourier transform of that, and you calculate the density function. You take the density fluctuation at the same time. This is very important. And if the system is in equilibrium, it is independent of it is not exclusively time dependent. This will become time independent, and this is called the static structure of the system. On the other hand, if there are different times, it may become only dependent on the difference of the two times, which is called time translational invariance, but it will be a function of the space or the Fourier transform that and QT. It is this kind of correlation functions that become very important. Now, a typical example of this in a fluid is like this, that you have a fast peak, and in this one, what does the fast peak means? It means that you have a central core and particles cannot penetrate beyond that. So you have a certain peak in the accumulation of particles at a distance which is equal to when the centers are at a distance equal to the hard spheres, or equal to the hard core, and that gives a peak, and then there are successive peaks after that. So this is generally the static structure of a disordered system. On the other hand, like if it is a time correlation function, as time goes, these two, what happens as time goes, if the system is normal, then this product, as time gets widely separated, becomes the product average becomes an average of a product of the averages. So here it is the average of the product, but if the two times get very separated, the usual probabilistic theory, the two fluctuations become independent, and so it becomes a product of the two averages, and by definition that is 0. So over long time, as the two time separation becomes very large, this decays to 0. So you see this sort of decaying behavior of this dynamic correlation function. You see this sort of hardcore peak and this in static functions. This is typical of behavior of this. And we will be talking more of systems which are strongly interacting liquids. So the thing is, it keeps this structure, but it changes drastically this structure. And that is what we will discuss more. One of the things that happens in this system, like this liquids or this thing, I was discussing the disordered liquid going into a crystalline state, is this sort of a freezing. Now, here I've drawn a very schematic thing, and such things were studied in computer simulations of system around 1960s or early 70s, when computers became more and more powerful. People started simulating such a collection of hard sphere in the system, and because if you take the potential as a collection of hard sphere, and then it is you can solve those equations in a computer. You take a large number, nowhere like 10 to the power 23, but large number of particles, and you simulate them. What you see is, as you change the density of, or as you change the volume, reduce the volume of this collection of hard sphere, at some point they sit into a FCC structure, face-centered cubic. Here I have drawn that schematic form of this. As you know that we study in elementary solid-state physics also, that a FCC structure is a closed packed structure. So if you take spheres like this, and this is where I have shown the picture of just one unit cell, this is how they will be packed. This is as close as you can pack them. When you pack them like this, like the spheres, this hemisphere and this, 1/8 of the spheres, they touch each other. This is the closest packing of a system of spheres that you can make. Now, when you take a system of hard sphere, it also freezes into a structure like this. But the difference is, when it freezes into a structure like this, if it is close packed, then the close packing structure is 0.74. That means almost 75% of the volume of the system is occupied by the spheres. It is easy to calculate this, very elementary. But what happens when you actually computer simulate this, it doesn't go up to that packing. It freezes even long before that. It freezes about 50%, instead of 75% roughly. It freezes almost when the system is 50% packed up. That means this distance A will be much larger than this, almost by 30% larger. This means that physically what is happening is, you have a system, bunch of hard spheres, and you keep compressing them. Once you have made 50% filling, they do not like to move around all around. They just start vibrating around their mean position, which is like this, but much more looser than this. It is not happening just because the particles cannot move any further. They can still vibrate, but you have a competition between entropic and interaction contribution of these two system of this system, that at beyond a certain density, the system likes to be in the FCC structure. So it has crystallized. That's what we say, crystallization. This is a very unique transformation of systems, very fundamental. That is called rigidity transformation. That means if you take the position of any particle, it is now sitting over some central lattice. This is the point I was telling earlier, with some displacement. You can define strains in this way. And the system now is such that the particles are vibrating around their mean positions. They do not move around everywhere. They vibrate around their mean position. So in statistical physics, this is called kind of an ergodic situation, where all the particles can go everywhere and they move around. So there's complete free movement in the system. If the particles get localized, the coordinate of each particle become localized. So this is a very fundamental transition, in the sense that if you think of a liquid, it is very easy to make relative displacement between 2 points. It is the relative displacement now it gets very, very hard to do when the system is crystallized or when it is rigid, because the basic lattice structure remains, and it gets very difficult, or it costs much more energy to for relative displacement between positions, and this is what we called a rigidity transformation. This rigidity transformation, or it's the liquid to solid transition. That is something I'm going to just discuss in a minute. But it can also happen that it does not go into a FCC structure, but gets almost frozen into a random structure. And these kind of systems are called glasses. Whereas we, as I will tell you in a minute, that we do understand to some extent using thermodynamic models, when it is a crystal, how this is transformed. But why it freezes into a glassy state where the rigidity or the system is almost like a solid, very, very long time to break the structure, but it is nevertheless a completely equilibrium state, or nor is the order very long range, which is in glass. Why this happens, this is still an unresolved question of condensed matter physics. There are many different inputs and developments. I'll just discuss a little bit of that. So, for the liquid to crystal transition, let us look at that. And this is the Ramakrishnan Yusuf theory, a cornerstone of this kind of physics. It was done by Professor Ramakrishnan and Yusuf from IIT Kanpur in around 1977. So basically, you use second law of thermodynamics for free energy minimization, but you do a continuum model. That means you take the density as a parameter and as a field. So you use rho as a function of x, and then you write the free energy as a sum of two parts. One is if the particles are not interacting, what will be the density field and what will be the corresponding free energy. So this is non-interacting system, and then you include the interaction in the system through this. This part is written in terms of direct correlation functions of classical physics. This free energy is named in the literature as the Ramakrishnan Yusuf free energy, which is used in many studies of theoretical liquid state physics and experimental also, and this is experimentally measurable quantity. And what Ramakrishnan and Yusuf did, started with that, a whole area, that is you study for different density fields and you see when the free energy will become minimum, because then you can say that this is the lowest free energy minimum state, and then you will have the liquid to solid transition. So it is in a particle picture as if you have the particles are localized in this position, but you describe the system in terms of a continuum fields. I'll just give a very pictorial sort of impression of this model. But before I move into that, these kind of models not only are limited to liquids to solid transition, it is used in study of liquid crystals. This phase field model. So instead of taking the density as a combination of many different wave vectors, very basic structure of the symmetry if you keep, you can study things which is like a poor man's density functional theory. The phase field models, solidification in metallurgy, there are lots of studies with this sort of model. So what is the basic ingredient of it? So you take the density, you test the density with a function which is like a Gauss. So you sum this, so Ri is each of the lattice sites, and you sum this Gaussian function at each site. So when you write rho r as this, you are basically taking, suppose there's a lattice, and then you are basically taking around the lattice a Gaussian density profile. And by this form, the width of this Gaussian is proportional to root over of 1 over root over of 1 over alpha, the reciprocal of that. That means as alpha becomes very small, this width becomes this density profiles around each center become very broad, and so all of them combine and you have an average uniform density. So alpha going to 0 would mean a liquid state, and alpha becoming large would mean a more localized state. And what was done was they tested the free energy with different structures, and what was found was that the FCC structure crystal beyond a certain density becomes the most stable state. That means its free energy is minimum. So if you are considering a model where you calculate a rho using, you take the rho in this and you choose alpha as an input, and then you calculate these functionals, the free energy, and then you test for at a given density, or if it is a different kind of interaction, not hard sphere, at a different temperature, how does this free energy changes? And then you compute the free energy as a function of temperature. Sure enough, it shows that beyond the freezing temperature, the crystalline state, the FCC crystalline state has lowest free energy. So this continuum models of equilibrium density is useful in understanding disordered liquid to crystal. Models used in this sort of thing are also used to calculate the elastic properties, of the system. Lowen and others used in 1999 on this. Not only the liquid to solid transition, this kind of models were also used to study amorphous states. Remember, this underlying crystal, if it is instead of FCC, if it's a disordered structure on which you are setting this density profiles, you can study how the free energy of an amorphous solid will go. And this has been studied by different authors, including myself with my student Charan Kaur, that you find local minima of the free energy using this kind of models. So as you go below the freezing density, there are metastable states, and you find the metastable minima with that. Nevertheless, it should be mentioned here that those local minima of the free energy does not give rise to timescales of a real class. It is a relatively low free energy. So you can interpret it as also as a liquid kind of transition for the amorphous state. Now let me talk, going from the crystalline state beyond that, let me talk a little bit on the glassy state, which is a key interest of mine over many years. So the supercool liquid, that means you have crossed the liquid to crystal density, you are below the freezing point. Freezing means liquid to crystal freezing point. And the system is no longer stable, because if it has to be stable, it has to crystallize. So this is called a metastable state. What happens is you create any kind of fluctuations in this system. That means you disturb the system a little bit from equilibrium. The time it takes to relax back to equilibrium would be very, very large. Like in the initial graphs, I showed you the time correlation function. So it takes longer and longer time to relax back to equilibrium. The viscosity of such a liquid gets increasingly high. So it takes increasingly longer time to equilibrate, and generally the viscosity on this are inversely proportional to the relaxation time. So it takes the system very, very long to relax back to equilibrium. And then there is a point at which the relaxation time becomes larger than the time scale of the experiment. This is generally taken like 100 seconds. But think of it, even if it is another order of magnitude higher, if it takes days for the system to equilibrate, it is impossible beyond that. You have to wait beyond that years to equilibrate the system. So these kind of systems are called amorphous solids. The basic question is that here is this ergodic liquid where the particles are traveling everywhere. The system develops a glassy state where the particles are almost localized, and it has a finite elasticity. So can a theory of this kind of systems be formed with microscopic description? Now, the key question in this is that is there an underlying transition which is a kind of phase transition? Earlier, what I have talked as phase transition is when the system goes from a one thermodynamic phase to another thermodynamic phase. In this case, what is happening is the system is increasingly slowing down, but it is still, if I look at the system is very much similar. Let me give an example. If you look at a glassy state, so crystallization is avoided, it continues to remain in the disordered state. Its structure factor remains roughly the same. This is in R space, the pair correlation function, the probability that you will see two particles close to each other. As you can see, up to certain distance, this is for a hard sphere system, so the potential is hard sphere. So two particles cannot be closer than their diameter, so that is why the probability is 0. But then it picks at a certain height, because two centers, it can form a ring around it. Then there is a minima because certain volume is excluded, then it is the maximum, so it oscillates like this. But this is an amorphous. For an amorphous system, it will happen like this. What happens in the case of a glassy structure, this form remains roughly the same. It does not change much. So as the liquid is cooled, the system slows down. The particles, but the particles remains very much like an amorphous system. So if you look, by look I mean, if you can see the structure of the distribution, then it is roughly similar to a liquid. Only thing is it has become very dense. Whereas if it is in a crystalline state where you have long range order, you will see Bragg peaks, that means reflecting the symmetry of the crystalline structure. So there is a very basic difference from the amorphous solid from the regular solid. Also, this is not an equilibrated system beyond a certain point. So this is the key issue, that whether it is a phase transition, what sort of phase transition, or is it at least approaching some kind of a terminal phase transition, a situation where the system is completely frozen. To study this, as you can see, time is now coming in, because the system is not like this, it is like this, but over longer and longer time, if I wait, the system will equilibrate. Of course, beyond a certain point, it is impossible to wait, so we call it glass, but it's not a completely equilibrated phase. So time comes in. So these kind of models were then thought of, so of being studied using methods of generalized hydrodynamics. Earlier we have talked about density as a function of space and time, and then I talked of density functional theory, where it is a function of local variable only. Now, in a fluid, in a many particle system, as you can see, the mass density is conserved. I called it n earlier, but m or n. The total momentum is conserved. I have not written energy just to keep things simple. So these are totally conserved properties. So in terms of this, we can define local fields. And in terms of these local fields, we can operationally define like this theoretically in terms of delta functions like this. What is the meaning of this? If I integrate this function over a little volume around x, then it will give me the total mass in that little volume. It will give me the total momentum in this volume. These are a bunch of delta functions. But as we know, these are not smooth functions, because these are delta functions, they are not exact functions. So to get really the physical density or momentum density local, I have to average this over all positions of R alpha. This is what we call an average over some distribution. Now, what distribution? If the system is not in equilibrium, it has to be a non-equilibrium distribution, or at best in hydrodynamics, it is done with a local equilibrium distribution. But even before that, one can actually take this equation, because this is the total number of particles or momentum is conserved. You can write down balance equation like this. These are exact equations. This is just a statement of the fact that this thing does not change in time. Or if it changes in time, we have to put on the right hand side those fluxes. But this is a balance of or conservation of those equations. From those equations, we can average this density fields, like the A are this rho or G. If I average it over non-equilibrium distribution or local equilibrium distribution, these are coarse-grained equations, and then we get the equations of hydrodynamics. That means for the average values of rho, average values of G. So this continuum mechanics equation become a starting point or use of studying dynamics of fluids, how over long time, long distance they behave. And not only long time, long distance, even over short times, it can be used to study. So here I have written the momentum density equation. So this is the momentum density equation, and one writes the stress part into two parts. One is some noise part. The noise enters because you write it in that way, so as to, this is a particularly useful way. First, I think, was introduced by Landau-Lifshitz. This is what I call Landau-Lifshitz methods. That it was it's a way of averaging over the system. So when I average this stress function, I get a contribution which is random. I put a contribution which is average, which is similar to averaging over initial states, and I get I can calculate correlation function. So this is a suitable method for calculating correlation function. In addition, this sigma ij can have a reversible dynamics, which gives Euler's equations, and then there's a dissipative equation. This equation is nothing but what we call Navier-Stokes equation in classical hydrodynamics. And like the reversible part will have pressure and the usual Navier-Stokes term, and then there's dissipative term. The dissipative term is the key thing in our case, that the dissipative term, because we were discussing more about glassy systems and viscosity, this is where the viscosity enters. And because by the very structure of it is viscosity is a rank 4 tensor. Now, in normal liquids, isotropic liquids, there we know of only two transport coefficients: viscosities, bulk viscosity, shear viscosity, and that happens because the system is isotropic. But just to indicate the strength of these equations, you can describe many different systems with it. You can describe liquid crystals with it. Then the eta ijk will have less symmetry, and you will have many components of this eta ijk depending on the symmetry of the liquid crystal, whether it is pneumatic or smectic, or it can even be solid. You can take solids. In case of solids, of course, the set of equations get extended by extra terms which we are called Goldstone modes, because there are broken symmetries in the system. But these, because to keep in line with the main theme of this talk, that these continuum models become very useful in studying in terms of very few fields and their partial differential equations, the effect of non-local. That means because those functions can be functions of space, and not only non-local, because there are non-linear terms in this. Non-local and non-linear terms becomes very easy to study with this. This is the general equations of, let's say, fluctuating hydrodynamics. Now, these transport coefficients, if I study the dynamics in which only short time dynamics is taken into account, then it does not account for the behavior we see in the supercooled state. That means the viscosity does not show that kind of increase that we see in a real system. Now, in a real glassy system. So to study this, we want to extend this to situations where we can take into account effects of stronger interaction in the liquid, because this is a strongly correlated liquid. when it is very dense and super cooled, the relation between each particles, the motions are much more correlated. And so to take into account, we extend the hydrodynamics, fluctuating hydrodynamics. Fluctuating, there is a noise, which is called nonlinear fluctuating hydrodynamics. And what do we mean by that? One can take the, let's say, this is the simplest example of seeing it, that if you take the, let's say, density, we take the time transform of it, take q going to 0, this will go to 0. So over longer distance or small q is the wave vector, that means it refers to variation of rho over long distance. So if we write this will, over longer distance, it does not change. Now the issue is, we want to extend it to nonlinear hydrodynamics. That means if rho is a slow variable, rho or phi, can I take products of those fields, like theoretical models in which phi is a slow variable? If can I take psi square, psi cube as slow variable? That means rho square or rho times some other fields, momentum, density. Can those be slow field? So this will be like coupling one mode with another mode. That's where the term mode coupling comes. So if you want to investigate that issue, then one should look at, like we look at this, that this is 0. This is 0 exactly by the continuity equation. But now, if I look at this quantity, as you can see, if I do a little bit of algebra, it becomes like this using the continuity equation. And so the equation becomes like this. So like this is 0. Is this 0? No, it is not 0. Of course, this quantity doesn't automatically vanish. But if I look at the long time behavior of this integral, then it becomes very small. Why? Because for long time, g and rho will be dominated by small k values, because over long time only small k values of rho and g survive because of this kind of behavior. So because only small k behavior survives, because of this factor of k, this integral will become small over longer time. That means as I go to longer time, smaller and smaller k becomes more important. So you in a sense, you include effects of different length scale and time scale by including such products of local fields into your theoretical formulation, and this is why it is called nonlinear fluctuating hydrodynamics. So these are continuum models with stochastic equations useful for study of non-local and non-linear effects. So these kind of systems, this transformation from an ergodic to a non-ergodic system was studied with this using collective density correlation functions, stacked particle density correlation function. Collective density correlation function I talked about earlier. Stacked particle density correlation function is a similar thing, and that is like how you link a single particle's motion instead of looking at the collective density. And one of the order parameter of this is the product of this density correlation function I was telling. Let me skip longer details of it. One of the things that happens, this collective and single particle, this is more recent, that the collective density correlation function and this thing affects the viscosity, the shear viscosity, whereas the single particle one is more related to the stacked particle, a single particle diffusion. It's a general relation in fluids that the viscosity and single particle diffusions are related. This is what is called the Stokes Einstein relation in hydrodynamics. With using these sort of models, this kind of things has been studied. One of the things that is seen, that is that if I take a dense system like this, if I tag a, let's say, black particle, how it is diffusing, the diffusion constant, that quantity and the viscosity, these two are related through this Stokes Einstein relation, as I said. But are they, earlier it was thought that they are exactly behaving similar to each other. So they are more like the Stokes Einstein is followed. But as we know in general in glassy systems from experiment, that Stokes Einstein is often violated. So this is something I looked at with my students Madhupriya and Nita Bidudi. These are two long papers in physical review in 2015, where we showed that the TAC particle motion is different from the collective motion. And we sort of predicted that the decay of the TAC particle correlation will be different from the decay of the single particle correlation. And instead of going into the theoretical details, let me show you an experimental result. This was an experimental result, came out much later. I saw this was done by Professor Ajay Shud and his collaborators. This came out in Nature Materials, I think, in 2018. And here they actually calculated those correlation functions from experiment. They looked at, there is conformal mapping methods where they actually look at particles and calculate. Here QC is the C is for the collective and S is for the single particle. So this is not computer simulation, this is actual experiment where individual particles are tracked, very careful mapping of the positions of the particle and then calculation of correlation functions. And what was seen is that whereas the collective correlation function goes here, this y-axis was shifted for each of these systems. It's the density that is increasing on the average. So you see that on the average, these over long time, the correlation functions are freezing some non-zero value. So this is 0. Whereas in the self-correlation function, they decay out more or less to 0. And this is something, this was in 2018 they found. In 2015, we said that we showed that the non-portability of the algorithm, this is more about theoretical again, but the freezing of the long time limit of the density correlation function, collective density fluctuation goes to a non-zero value, whereas the TAC particle correlation function still decays to 0. So the single particle motion was quite different from the TAC particle motion, and this is something that was predicted from study of the theoretical models and then actually seen in experiment. Let me now go beyond a little more on this, that these kind of model that I have talked about using fluctuating nonlinear hydrodynamics and all that, mode coupling, it does not really explain the very high increase of viscosity or the complete freezing of the system. This is what has been termed in the literature as spontaneous breakdown of ergodicity. If you think of these phenomena that I have been describing, so far I have already always formulated the theory, whether it is dynamics or statics, around the liquid state, a little bit fluctuation around the liquid state, then how does the fluctuations correlate with each other and all these kind of effects. At high temperature, near freezing or melting point, not too much below the melting point or freezing point, this kind of fluctuation around a single liquid state minimum is quite applicable and works. But as the temperature gets very low or the system gets extremely dense, then such models starts to break down, and there is an entropy crisis in the system. The system completely starts getting frozen. By entropy crisis, I mean the number of possibilities it has in front of it becomes less and less. This is quantified in terms of configurational entropy or complexity. What is meant by that? That is something that if you think of this system going into a free energy landscape description, just 1 second. If I go to a free energy landscape description, just 1 second. Then if there is a liquid state minima that kind of controls the behavior at high temperature, then there is a crystalline state minimum of the free energy that controls the behavior at below freezing. At deep supercooling, there are many other minimum of free energy that exist, which may be higher than the crystalline state, but still they can become very deep. And as the number of options for the liquid increases, that means you have many such minima, the system tends to get locked into one of those free energy minimum and then remain in that for a very long time. Now, if I take the number of such free energy minima or options possible for the system to be a number n, then log of n gives us a measure of entropy, kb times log of n, and that is called the configurational entropy of the system. These kind of things can be studied. Experimentally, what does this sort of behavior indicate? One of the classic description of liquid and gases is this angel plot, where you plot the relaxation time versus Tg by T. Tg is this glass transition temperature. That for each system you divide the temperature. So by definition, then the viscosity is 10 to the power 12, or the time scale is 10 to the power minus 2 seconds or so. So all the points here are together, and then different system goes there in different way. Systems on this side, where it first goes slowly and then suddenly hits up, these are called fragile systems, these are called hard systems. But one thing is seen very clearly, that there is a behavior which is like a Vogel-Falcher kind of behavior. This kind of behavior is generally called Vogel-Falcher, where the system tends to as if it is diverging at T0. This sort of thing is universally seen in glassy systems. These sort of studies were more pinned by using a different kind of plot, the same data. You take the tau alpha and tau alpha by the corresponding tau alpha using the Vogel-Falcher form for this is lower temperature. So this is the plot of this. As T gets closer to Tg, this becomes smaller, and so and then you see this thing is more like Vogel-Falcher. As you move to higher temperature, it moves away. This is where MCT and all these are more applicable, which I was talking about. But this is the range where the system is starting to behave differently. This thing where it is straight increasing by a Vogel-Falcher kind of form. How to form theories of this? So these are the two behavior that I just mentioned. There is the power law type behavior. Away from this is where the mode coupling and all these models, and then the Vogel-Falcher form. To understand those, one can use again a similar kind of model as we used in density functional theory, but you calculate the free energy now for a very different system. It has a way of calculating. It has this spontaneous breakdown of ergodicity that I mentioned. That means it has many free energies. So you have to calculate it using that trick or that input, that there are many free energies, and you devise. And this was due to Remy Monasson in 1995. We first said this, that how to calculate the number of such minima so that you can calculate configurational entropy and all that. This is a very classic paper. Later on, Parisi and Mazard and those people also studied using this model. So here you are trying to again calculate the free energy like a density functional theory, but for the broken ergodicity system, where it is very deeply near very high viscosity and very deeply frozen into metastable state. This calculation of this free energy requires techniques which are called replica. It is not the replica of method of, it is not, I stress, it is not the replica method of Parisi that was used for spin glasses, which is a completely different story. This was first developed by Monasson, and it works very nicely to calculate this. I have been working more recently on this with one of my students, Prakash Bardhan. I'll mention a little bit of his result. So what you look at is there are replicas of the same system, and you calculate correlation functions. From that, you study how many such minima are there. And so the density functional is the same density functional theory model that we use in that Ramakrishnan and Yusuf use. Only thing is you need to keep higher order correlation. That means not only you keep two particle correlation, you also keep 3 particle correlation and so on. And then you calculate order parameters similar to what we studied in mode coupling, but now it is between replica, not like different time, but between two different replica. When the intra-replica, when the same replica, this is like, the correlation is like structure factor. But the intra-replica correlation, that means different system remains even connected in the same free energy minimum, completely frozen sort of situation. That is A not equal to B. That is what is more characteristic of the glassy state. And these equations were studied. You can calculate the configuration entropy. You can show that there is a Kauzmann temperature or Kauzmann point beyond which even the configuration entropy goes to 0. That means the number of states become sub-extensious. There is another relation of glass physics, that is the relaxation time the system is related to configuration entropy in this way. That means if the configuration entropy goes to 0, relaxation time becomes infinity. That's the Adam-Gibbs relation. So using this method we calculated, we use the input, the equal time, the in-replica correlation from static structure of the system, and we calculated the configuration entropy. Correctly writing his thesis. This work is soon to be reported, that we see the configuration entropy for different kind of inputs. Of course, these are different. This is one is with Perkasiewicz structure factor, the standard liquid state inputs. This is a structure factor we used density functional structure to calculate it, a frozen structure. This is the Roger and Young structure factor. For different structure factor, you see the configuration entropy coming down. So the picture that emerges that initially there is a large number of, there is one single liquid state minima. Then at some point, there are lots of local minima. But as you increase the density, the number of local minima keeps coming down, and you see this approaching towards a ideal sort of situation where configuration entropy goes to 0. So this is what is called the mosaic state of glassy state, where you have many such local minima of free energy, and the system goes into a random first order transition. That means in different parts, it transforms into different minima, and you have a mosaic of such states. And if the system gets, there is some critical length L. If R is greater than L, then the fluctuation no longer survive in a particular state, and the states gets, it does not extend any further. The system will have many such evolving patchworks of glassites. By glassite, the authors, this was an argument put forward by Biroli and Bouchot, that glassite is a term used for crystalline states, and so this similar to polycrystalline structure, and this is called the mosaic state. I'm almost done. I'll just say a few things about the active matter hydrodynamics, which is more of my very current interest. That you have Brownian motion of these particles. There is Vishek model, which is very well-known model in this, that where you study random inputs into a system and it evolves in time. This kind of model was used by Toner and to model with hydrodynamic equations. And this is the last thing I just want to mention a little bit. That is that the hydrodynamic equations now look like this sort of equation I have told you earlier, the generalized Navier-Stokes. Only thing is this part shown in blue, these two terms, these are new in this model. So this is a description of a flock of birds, or a stream of bacteria, something which is moving with an average velocity. And what they showed from the analysis of these equations is that when the average velocity is beyond a certain value, then the system kind of freezes into an ordered state. So think of a flock of birds which they together move in a certain direction with an average velocity. They are not dispersed. How do they are not colliding with each other. How do the hydrodynamics of this go? So now you are no longer talking of hydrodynamics of particles. You are talking about hydrodynamics of a selection of quote unquote particles which are themselves generating energy. Each bird is moving in its own way, but it is it is coordinating its movement by looking at the other one. So the effective kind of equation of motion between them is different. Toner and Tu wrote down those equations and analyzed those. They basically wrote down these equations from intuition. They modified this term with usual hydrodynamic terms and then studied it. My intention here in last 5 minutes is not to go into those discussions, but how does this equation come from the basic statistical mechanics? Now, remember, this is not an equilibrium system. This is not even a thermal system. There's no temperature in a flock of bars. It's just a mechanical system. But can we apply? They applied the hydrodynamic equation with extension of models like this. Can we get this from equations of the basic equations of mechanics? Again, a theme of this talk. One of the approach of this was to deduce this hydrodynamic equation is the Boltzmann equation approach. That means you take the Boltzmann equation, which gives, this is generally used in fluids also for kinetics of particles. So you take the microscopic description of the particle. F is the position, the probability that you have a particle at position R, at position R at time t. Here, of course, the particles are moving in different directions. They consider it in 2 dimensions. So there's an angle, theta, and this, they looked at the equation in this form, and the number of particles moving, if you average over all directions, that is the average density at that point. The velocity is given by this. They looked at those equations. These are papers written in 2006, 2013 by Eric Bartin is one of the main architects. Then there are a lot of other people, some people from India also involved, Sudha Misra and Sridham Ramaswamy. So these methods were used. What I did is, I did with my student, use the classical Brownian, the active Brownian motion equation to get those equations. And so we take the Brownian motion equation, but now you see, compared to what I wrote down last time, these 2 terms are the same, but the dissipative term, I've taken it to be momentum dependent. So earlier, this is a constant, a normal Brownian motion equation. Now I have taken it to be momentum dependent and chosen its momentum dependence using standard form like detail balance and the P minus P, the tensorial structure, and P minus P symmetry and all that. When I put that, then I take this equation and then I use similar sort of methods like local equilibrium averaging and all that to calculate the hydrodynamic equation. So this is the frictional term in detail, and I average over local equilibrium distribution. Now, note here that the local equilibrium distribution does not involve any temperature or anything. Beta is here, just a constant which will give you the average velocity. It is not the 1 over kBt, but there is a chemical potential related to the number of particles. So when I average this equation in a macroscopic way with local equilibrium distribution, we showed that you actually get the Toner and Tu equation. So starting from a microscopic, we could obtain the hydrodynamic equation. This is a paper with my student Sunil Kumar Jadhav, who has now graduated, and myself in physical review in 2018. So the noise correlation involves, of course, the density. This is the noise, and it came out from our calculation naturally that it is multiplicative. Generally, there is a breaking of Galilean invariance in those systems that also can be produced from some such studies. So I've taken enough time. Let me just summarize. We have discussed continuum models in terms of local fields, density functional models of freezing, extension. So I have discussed density functional model of freezing, Ramakrishnan Yusuf, how a continuum density can give rise to this. We have extended the liquid state dynamics, ergodic, non-ergodic transition below freezing point that occurs from coupling of densities, which we again formulate using continuum models of fluctuating hydrodynamics, mode coupling approach, and all that. Then I discussed briefly on the replicated liquid state and calculation of configuration entropy, how the free energy landscape fragmentation model can be used to study a continuum description using replicated liquids to calculate the configuration entropy. This gives rise in a natural way to the mosaic state or random first order transition with random first order transition. Finally, I have told you very briefly on the active Brownian motion. Again, equations of continuum hydrodynamics can be obtained from microscopic equations of active Brownian particles with modified frictional coefficient for this non-Hamiltonian self-propelled particle system. Thank you for your attention.
Thank you, Professor Das, for so informative talk on mechanics of many discrete and continuum description. Now the presentation is open for questions.
Vinod?
Yes, yes, sir.
Can I ask a question?
Yes, sir. Yes, sir.
Shankar?
Yes.
I have a question in the beginning of your lecture.
Yeah.
You took the density distribution to describe the transition, density distribution to be a Gaussian.
Yeah.
If you take some other distribution, what will happen?
Well, see, here I kind of
suppose it is a Lorentzian.
Yeah, I know what you're saying. Let me answer it. I sort of this is what you are talking about, right? The Gaussian distribution. Now, here I have gone a little broken a little bit of historical continuity. This Gaussian distribution was actually offered by Tarazona. Now, when Ramakrishnan TBR did this, they did not use a Gaussian approximation. What they did is they used an expansion in terms of the reciprocal lattice vectors. So that's expansion in the reciprocal lattice vector space, and you keep reciprocal lattice vectors up to different terms, and then you do it. So you can do, and that is more exact because you are no longer doing any approximation of any parameter or anything. Now, the Gaussian approximation works fine, and the physical picture is very clear because you get this profile. But it should work with other models. But the Gaussian model is just an convenient.
I got it. I had forgotten that expansion reciprocal lattice.
So that was originally used by TBR. TBR and Stokes.
I had known that, but I have forgotten that. Now, second question. What about these theories which you are talking about in the hydrodynamic limit? What about, you can say, when the wave vector becomes, of the interparticle distance level,
Now, that is why
the liquids are behaving, one second, liquids are behaving differently, various liquids, like liquid metals and inert gas liquids. Their behavior has been very different, and lot of experimental data are there also. So, what is the current picture? You may be more aware of that.
Yeah. Well, one general sort of comment to that, this idea of long wavelength and short wavelength.
That is what you are doing.
Yeah. So let me answer that. So what happens is these systems, if you look at the mean free path of the particles, they become so small, they almost go near the first minima. The inverse of that goes to the first minima, first maxima of the diffraction peak. So even so, the mean free path becomes so small that you can still satisfy that it is larger than the average distance because the density is also very high. So this is why I use the term generalized hydrodynamics. That's one thing. The other thing is, if you use continuum mechanics methods or you use basic kinetic theory methods, you are basically calculating finally the same property. So it is true that at large scale, things can get different, and only fluctuations up to certain length scales are taken into account. But it works at high density to fairly large, fairly large wave vectors. That's the only thing I want to say. That, and eventually all these effects does win out to long length scale or small k. But there is an approximation involved in it, and this is at the very beginning. If you noticed, I said that this is a general problem of liquid state physics, that you really do not have any small parameter where you can say quantitatively accurate statements. So a lot of these theories, the mode coupling theories and all that, this is a common mistake a lot of people make about it, that the quantitative accuracy of these models a lot of time are not very good because of the very problem you are raising, that the short wavelength fluctuations are only taken into account in an approximate way. So that is basically the answer I can give.
But other way around, it is easier to come from the kinetic regime to the hydrodynamic.
Yeah, so that's what I said, that these kinetic theory models, when you look at this, like you use Zwanzig projection operator and all these techniques, what happens is you basically end up with the same equation. Because when you use this Zwanzig projection operator, all that, when you really want to get to some level of calculation, you have to do approximation. The moment you make the approximation, there is no way out rather than reducing it to integrals of the form that you get with the continuum mechanics. Only in the continuum mechanics case, you get a more controlled way of doing the calculation because of using certain field theoretic methods, Feynman graphs and calculating that. So it is more organized instead of making an add up. But so far, the results are not very different. The only way you can improve it is by going to higher order calculations, and some efforts have been done, but it gets so complicated that people have not really done any practical calculation. You look at the practical calculation, again, some sort of approximation is there.
But do you believe that means there are the phonal-like excitation near the interparticle distance wavelength?
Possible.
Hydrodynamic. Well, there are experiments. Only I think the liquid metals are having the property.
Yeah, but
which I measured by rubidium and.
Yeah, but those excitations are not affecting the glassy state, right?
No, not glassy state.
Yeah. So those models can be handled with microscopic models, Boltzmann level and all that. But for long distance and getting the system into a completely frozen amorphous.
Anyway, that is a.
That's a different problem.
Different problem. But I want to tell you that you start from Liouville operator and construct binary collision theory for continuous potential.
Yeah.
And when you take the potential to be hard sphere, you recover Inskog result of transport coefficients.
Right.
I have done this and in that paper.
These I know. Those methods are useful for studying the kind of effects that you are mentioning. They are very effective for that. But for calculating really strongly correlated systems where you have very cooperative motion, that's why all this idea of Goetze and all this came, that the mode coupling and looking in a self-consistent way and calculating effects which are in a feedback kind of scenario. So those things will be useful in getting a complete freezing of the system.
But I think you have given the impression, I think everybody must have got glass will melt away after some time.
Yes.
So
if I want to understand the complete freezing of it, those kind of things or configuration entropy going to zero, that's why I talked about
how many years? I have never seen in my lifetime of around 80 years glass.
What do you mean by that? 80 years what?
Because the The relaxation time is not stable.
That can be age of the universe. I mean, that can go to. Yeah.
Okay, the age of universe. Huh?
Yeah.
Okay. Okay, very good talk.
Thank you.
Any other question from the participant side? So if there is no more question, let us thanks once again Professor S.P. Das for such a wonderful lecture on this short-term course, Current Trends in Condensed Matter Physics. So, so today in the evening section, we will be having a second talk by Professor K.N. Pathak at 3:30 p.m. So I request participant to join before 10 minutes, okay? And you are not allowed to join in between the talk because it takes a lot of chaos. This happens just now in the case of Professor Das also. Somebody has started presenting their screen and it was disconnected. And it will resume after that, but this happens. This glitches happens when we do online presentation using Google Meet. But this is not the case in Zoom or other software. So I request the participant, please don't press the present now button, okay, in the second session. So we'll meet again at 3:30, okay, and you have to join 10 minutes before. Thank you. Thank you, Professor Das. Thank you so much. Thank you, Professor K.N. Pathak, for joining the morning session. Thank you. Thank you, everybody. Thank you, all the participants. Thank you, sir.
Thank you.
Thank you, Professor Pathak. Okay, we will. Yes.
Close it. I'm
Okay.
unable to close. I'm
Sir,
unable to close.
you can press this, you know, the phone button, okay, the calling button, the leave call. Okay, so when you press the leave call,
Red one.
yes, sir, yes, in the center. Yeah, that's it. Okay.